Hello and welcome to our semiconductor video. Curious to know where semiconductors are used? One of the common places they are used is in electronic devices such as our smartphones. If you look inside a smartphone, you can see there are hundreds of electrical components. Many of these electrical components use silicon in their structure, such as the integrated circuit or IC. Silicon with its unique properties enables these elements to perform billions of operations simultaneously. Now let's take you inside a semiconductor to understand how they work. The importance of silicon was discovered in the early 19th century when the study of semiconductor materials began. But what are semiconductor materials? Here we are showing a portion of the periodic table related to semiconductors. The element semiconductors, those composed of a single species of atoms, such as silicon and germanium, can be found in column 4. To the left of this group, we have group 3 that are called trivalent, atoms that have 3 electrons in the outermost shell. The other column is group 5 that are called pentavalent, atom having 5 electrons in the outermost shell. In the early 1950s, germanium was the major semiconductor material. Since the early 1960s, silicon has become a practical substitute. The main reason silicon is used in semiconductors is that silicon devices exhibit better properties at room temperature. Also, silicon in form of silica and silicates comprises 25% of the Earth's crust. In this video, we will be only focusing on boron from group 3, silicon from group 4, and phosphorus from group 5. Let's take a look at the atomic structure of these elements. Silicon is a chemical element with the atomic number 14 and has 4 electrons in its outermost shell. Phosphorus, with the atomic number 15, has 5 electrons in its outermost shell, and boron with the atomic number 5 has 3 electrons in its outermost shell. Silicon is a classic semiconductor. Its conductivity lies between that of conductors and insulators. The reason for this is that in a pure state, silicon atoms share 4 electrons with adjacent silicon atoms. Hence, there are no free electrons. This is an example of an intrinsic or pure semiconductor. If a semiconductor device is made of pure silicon, it won't present practical properties for making a semiconductor device. Thus, we need to build an extrinsic semiconductor. This type of semiconductor is the one in which a silicon atom is replaced with a specific impurity in order to improve the conducting properties. This makes the semiconductor suitable for electronic applications like diodes and transistors. For instance, when silicon is replaced with boron, it forms 3 covalent bonds in the silicon structure and leaves a hole leading to the formation of a p-type or positive semiconductor. Also, p-type impurities are called acceptors. On the opposite side, when phosphorus impurity is added, it forms 4 covalent bonds which give free electrons to the semiconductor, which produces an n-type semiconductor. N-type semiconductors are called donors as it gives free electrons to the semiconductor. The process of adding impurities to pure semiconductors is called doping. To understand the function of a semiconductor in a device, we will use a simpler example such as a p-n junction like a diode instead of an IC, as it is more complex to explain here. First, if we have p and n-type semiconductors without a junction, the p-type material contains a large concentration of holes and the n-type contains a large concentration of free electrons. Let us now examine what happens when the p and n-type materials are made to form a junction in this animation. In the absence of any applied power source, there is no net current in the system and the Fermi level is uniform throughout the structure. However, the large carrier concentration gradients at the junction cause carrier diffusion. Electrons from the n side diffuse into the p side and holes from the p side diffuse into the n side. Most of the diffused electrons recombine with holes. As a result, a region is formed near the junction that has been depleted of mobile carriers called the depletion layer. Now if we connect the p-n junction diode to a power source and have the positive terminal of the battery connected to the p-type and the negative terminal of the battery connected to the n-type, this is called forward bias. When the diode is forward biased, the depletion layer that electrons need to overcome to enter the p side from the n side decreases. As shown in the animation, the increased carrier diffusion from the n side of the junction to the p side causes minority carrier injection at the edge of the depletion region. These carriers move away from the junction due to diffusion and will eventually recombine with a majority carrier. The majority carrier is supplied from the external circuit and hence a net current flows through the device. However, if the negative terminal of the battery is connected to the p-type and the positive terminal to the n-type, the diode does not allow the electric current to flow in the opposite direction. Thus, this makes a p-n junction diode a 2-electrode semiconductor where the electric current flows only in one direction. We only covered the main topics of a diode in this video to explain to you the application of semiconductors in real life. However, there are more details and definitions for diodes. We will cover all of them in our diode video. We hope you enjoyed this video. Please stay tuned for more videos by subscribing to our channel. Goodbye.